So far in our study of hydrocarbons, we have discussed how the number of carbon atoms in a hydrocarbon can affect the state of a substance at room temperature. Hydrocarbons that are solids have more carbon atoms. Those that are gases have fewer carbon atoms. We have also learned that the number of carbon atoms plays a role in the boiling point and viscosity of a hydrocarbon. More carbon atoms in the hydrocarbon, like motor oil, means higher boiling point and higher viscosity. Less carbon atoms in the hydrocarbon, like kerosene, means a lower boiling point and lower viscosity. During this lab, you will determine the amount of thermal energy released while burning several different hydrocarbons. Might there be a relationship between the number of carbon atoms in the molecule and the amount of energy released? That is what you will find out. As a class, we will investigate the combustion of 3 different hydrocarbon fuels: methanol, which has 1 carbon, ethanol, which has 2 carbons, and candle wax, which has 36 carbons. The combustion reactions for each fuel are written on the lab. Take the time to fill in the coefficients for each reactant and product in order to balance the reactions. Remember, a combustion reaction occurs when a carbon fuel reacts with oxygen gas to produce carbon dioxide, water, and energy. The purpose of this lab is to determine the amount of energy released upon burning 1 mole of the hydrocarbon fuel. This quantity is known as the heat of combustion, or delta H with a little c. To determine the heat of combustion, we will use the following equation. Delta H equals M, which stands for the mass of the solution being heated, times C, which is the specific heat constant, times delta T, which is the change in temperature of the solution. During the lab, the energy from the burning of the fuel will be transferred to an amount of water. The water will absorb the energy and change temperature. We will make the assumption that all of the energy released by burning the fuel is absorbed by the water, causing it to change temperature. Water has a specific heat constant of 1 calorie per degree Celsius times grams. This means that 1 calorie of energy is needed to raise the temperature of 1 gram of water by 1 degree Celsius. Since we know the specific heat of water and we can measure the mass and change in temperature of the water, we can calculate the heat absorbed by the water. Based on our assumption, this value is equal to the heat of combustion. Let's work through a problem using some sample data. Pay attention because these are the same calculations you will perform after collecting your own lab data. The first piece of data you want to collect is the room temperature. You'll be cooling the water sample to about 12 degrees below this temperature and heating the water sample to about 12 degrees above this temperature. You will mass your fuel source before burning any fuel and then again after burning the fuel. From this data, you can subtract to determine the mass of fuel burned, 0.27 grams in this case. The energy from the fuel will be transferred into the water inside of the tin can. So to determine the mass of the heated water, you will need the mass of the can and the mass of the can plus water. Simply subtract these two values to determine the mass of the heated water. Here we will get 118.49 grams. To determine the change in temperature of the water, subtract the temperature of the water before heating from the temperature of the water after heating. In this case, the temperature change was 21.8 degrees Celsius. Now we are ready to determine the thermal energy absorbed by the water using our equation. In this case, delta H equals the mass of the heated water, 118.49 grams, times the specific heat constant for water, which is 1 calorie per degree Celsius times grams, times the change in temperature of the water, 21.8 degrees Celsius. By analyzing the units for these values, you can see how the grams cancel and the degrees Celsius cancel. This means our numerical answer will have the units of calories. Multiplying these 3 numbers together gives us 2,583.082 calories. But hold up, that is way too many sig figs. Remember, when multiplying or dividing numbers, the answer can only have as many sig figs as the number with the least amount of significant figures. The mass has 5 sig figs. The change in temperature has 3 sig figs. Constants, like the specific heat constant, have an infinite amount of sig figs. This means our answer can only have 3 sig figs. Rounded appropriately, this means the delta H is 2,580 calories. Remember, we are making the assumption that the energy absorbed by the water equals the energy released by burning the fuel, also known as the heat of combustion. The heat of combustion has units of kilocalories per mole. The remaining calculations will help us determine this value. Let's start by converting from calories to kilocalories. This is accomplished by dividing by 1,000, since there are 1,000 calories in a kilocalorie. Keeping with 3 significant figures, this gives us 2.58 kilocalories. Understand what this value means. When 0.27 grams of fuel is burned, 2.58 kilocalories of energy is released. We are not interested in the amount of energy released when burning 0.27 grams. We want the energy released when burning a mole of the fuel. So in our next calculation, we must convert the grams of fuel burned to moles of fuel. For this sample problem, the fuel burned is methane, or natural gas. Natural gas has a molar mass of 16.0 grams per mole. To convert from grams of methane to moles of methane, simply divide by the molar mass. 0.27 grams of methane divided by 16 grams of methane per mole of methane results in 0.016875 moles of methane. However, that number has too many sig figs. Our answer can only have 2 sig figs. So that means we burned 0.017 moles of methane. Finally, all we have to do to determine the heat of combustion for methane is divide the kilocalories of energy released by the moles of fuel burned. Simply take the answer from the second calculation and divide by your answer from the third calculation. 2.58 kilocalories divided by 0.017 moles results in an answer of 151.7647 kilocalories per mole. However, our answer is limited by the 2 sig figs from the moles. The correct value would be 150 kilocalories per mole. You are about to watch the procedure for the lab using ethanol as the fuel. Write down the data collected during the lab, then determine the mass of fuel burned, mass of water, and change in temperature. With this data, you can determine the heat of combustion of ethanol by following the same steps outlined here. Without further ado, let's get started with the lab. The fuel we will use for this lab is ethanol. First, we will mass the ethanol container before we burn any of the ethanol. Be sure to record this value in the data table on page 4. Next, we will mass the can empty. Be sure to record this value in the data table on page 4. Now, let's get room temperature. Room temperature is 20.9 degrees. Make sure that goes in the data table. Next, we are going to add 180 milliliters of tap water to the empty can. Now we want to cool down this water to about 12 degrees below that room temperature we recorded. To do this, we will add a little ice. Once we have it cooled down, we want to record the temperature in the data table. Make sure 6.5 degrees goes in your data table on page 4. Now we want to remass the can with the water. We're going to dry the outside off really well, and then record this mass in your data table on page 4. This is the can plus water. Now we are going to ignite the fuel and use the ethanol to warm up the water inside of the can. We will continue to heat the water inside the can until it reaches a temperature about 12 degrees above that room temperature that we recorded. Remember, we are assuming that all of the energy released by burning the ethanol fuel is absorbed by the water in the can. That is going to allow us to determine the heat of combustion for ethanol. So you can see the flame produced by burning the ethanol is heating up the water in the can. Here is the final temperature that our water reached. Make sure you record that temperature in the data table on page 4. Now we will extinguish the flame on the ethanol burner. And now we will get the mass of the ethanol burner again. Since it's burned some fuel, the mass should be less. Make sure to record this mass in the data table on page 4. We have collected all the data for the lab, so now we can clean up. You will notice that there is some black residue on the bottom of the can. Try to clean this with a wet paper towel and think about what that residue is and what may have caused that residue to be there. Use the data that you have collected by watching this video to complete the calculations on page 4. Those calculations are just like the sample problems we worked on in the pre-lab section of this video. Then, answer the questions on page 5 and 6 to the best of your ability. When you have finished the lab, be sure to turn it in to the instructor.